So I want to cover a few mathematical ideas. This is the first installment of this kind. So we have some quantum mechanical system in mind, and we have a Hilbert space, let us say of dimension capital N, which may be infinite. This is of course the complex dimension because N is a complex Hilbert space. So vectors in this Hilbert space will be written in this way, psi, phi, and so on. Then the first definition is what is called the unit sphere in this Hilbert space. All those vectors which have unit norm. This set, this thing B has real dimension 2n minus 1. You can easily picture it. The important thing is that while script B is clearly a subset of the Hilbert space, it is not a linear vector space. All its vectors are vectors of unit length. Now, the group of phase factors, the group U1, acts on this set in an obvious way. If you take a vector of unit length and you multiply it by a phase factor e to the power I alpha, the result will also be in the same unit sphere. So this is the U1 action. Of course, the U1 group acts on the full Hilbert space as well. Now here I am using it in its action on the unit sphere. So next we introduce concept of the ray space, which I write as script R. It is the quotient of this B with respect to this U1 action. What we mean is that we say two vectors psi and psi prime which differ by a phase factor in this way should be regarded as equivalent. Or you can say the quotient views collections of vectors of this form with psi fixed and the phase factor varying as one object. So this is called the ray space. And as you all know from elementary quantum mechanics, the simplest way to deal with the ray space is to say that it consists of these projection operators onto unit vectors. This space also is not a linear vector space. It is not even a subset of the Hilbert space. You must appreciate this. It is of real dimension 2 into n minus 1 or complex dimension n minus 1, and in mathematical notation it is referred to as the space Cp n minus 1. So we have these three things: the Hilbert space, unit sphere in Hilbert space, and this ray space. Three things, and this will be a common theme in all that we do hereafter. So as I said, ray space is not a subset of H or B. It is constructed by this equivalence procedure or quotienting, and what we have is what is called a projection, a rule which tells you how to go from each unit vector to the corresponding point in the ray space. So this is always written as pi, and here is its definition. So I will draw a picture here on this right hand extreme, and I will try not to alter this picture during the course of this lecture. This is just to aid your imagination. The ray space is sitting down here. Up above is the unit sphere. This projection goes in this direction, and if you take any point in the ray space, it is the density matrix or the projection operator rho of psi for some psi unit vector in the Hilbert space. And now you can look at all those vectors in B which have this same image under this projection. So all of these are vectors which differ from one another by phase factors. So we say in this picture that this is a base, this is the full space, and all the vectors, unit vectors psi, which project onto a common image, they form a one-dimensional fiber. Many of you may know these terms, but for some it may be new. So it is a one-dimensional or a U1 fiber. So a fiber is something which is sitting on top of a point in the base or in the ray space. So there is a mathematical way to describe this whole fiber. What we would say is, let me write this equation so that you get used to the notations. Suppose you start with a point in the base in the ray space. From there you can go to its inverse, total inverse, which means the set of all the vectors in B which have rho of psi as their image under the projection. And this is easy to see. It consists of all vectors psi prime related to psi by a phase factor. The psi vector psi is kept fixed and the phase is allowed to vary. And this is, of course, in the unit sphere. So I hope this diagram is clear. All right. So today I hope to go a bit fast. So if there are any questions at this stage, I would like to try and answer them. So we have introduced Hilbert space, unit sphere in Hilbert space, ray space. And as you all know from the physics interpretation, points of the ray space are in one-to-one correspondence with distinct pure states of the quantum mechanical system. Now, so that diagram will stay for the rest of this lecture. I might draw a companion diagram on this side a little later. Now what I want to consider are curves in the space B. So I will use a certain notation, script C. What it denotes is a set of points in the unit sphere B parameterized by some parameter S, let us say running from an initial value S1 to a value S2. And it will be assumed that there are some conditions of smoothness on the choice, the way this curve is chosen. Apart from continuity, depending on the context, we may want to say it is once differentiable or it is twice differentiable. It depends on the use we are going to make of such a curve. But the basic geometrical object is curves parameterized with the parameter S lying in the unit sphere B of Hilbert space. Now, if you take such a curve and you apply this projection rule, or projection operation to go from the Hilbert space vectors to the race space, you will get an image of this curve, and that I will denote by not script but capital C, and clearly it is point by point image of the curve up above. So, this lies in the race space. So, soon I will draw a diagram to illustrate this. So, or maybe this is the point at which I should draw this diagram. It is very similar to what I have on the right hand board. What I imagine is a curve from a point, from some starting point in the race space, is sufficiently smooth for whatever purpose we want to consider, running like this in the race space, parameterized, and at a general point the parameter is S. It starts with the value S1 and ends up with the value S2. So, this curve I think I drew this too large. Here is the parameter. The curve itself I will call capital C. So, you can imagine here is the curve in the unit sphere of Hilbert space. This is the vector psi of S for parameter value S. This is psi of S1 and this is psi of S2. All right? And so it is denoted by script C. So now we say that if you are given a smooth curve in the race space to begin with, any parameterized curve in the unit sphere and in Hilbert space which projects onto this thing given in the race space is called a lift of the race space curve. So, every curve script C with a parameter projecting pointwise to a given capital C down below is called a lift of the thing downstairs. So, you can see that while projection is well defined, each point in B goes to a unique image, this lifting has a lot of flexibility, and the most general lift will be of this kind. We can have a curve C prime going through a collection of points psi prime of S, but having the same image when you do the projection, and the relationship will be in general applying a phase factor varying with the parameter at each point along the curve. So, let me write the relationship between C and C prime. Alright, so this is the general way, the most general lift of a given curve in the race space will be obtained from any one lift by making an arbitrary change of phase at each point in a sufficiently continuous manner, in sufficiently smooth manner. And exactly what it means by smooth depends on the context. We will see examples of this later. Okay, so I hope the two diagrams help you. Here is a curve in the ray space. Script C is one lift of this. C prime is another lift, and there are infinitely many lifts because you have infinite freedom in the choice of this phase factor alpha of S at each point along the curve. Okay. Now we go on to the next construction. Given the curve C, it is natural to define the tangent vector to the curve at each point, which I will denote by psi of S dot.
You introduced phi inverse from the left hand side.
Yeah, where? Here. Yeah.
So, you would have also said script C is phi inverse of C?
No.
But so you are taking one script C, you mean the particular curve.
A particular lift is one script C. C prime is another lift of the same thing down below. So, pi is a point-to-point mapping. So, pi inverse is to be regarded, it is called the total inverse. Given an image point, what are all the points that are up above which are mapped into that given? That's called the pi inverse of the given point. But for a whole curve, it's not, may be confusing to use pi inverse. That's my feeling.
Or some students may be seeing this ray space for the very first time.
Yeah.
So let me ask you
Yeah.
a couple of other things.
Yeah, please.
You could have also written rho of psi e power I alpha psi is equal to rho of psi. Right?
Yeah, correct.
And some people may be more familiar if you say R is V over U1 versus U1.
Yeah. So I should have written it here. Yeah, maybe I can add it here. Correct? You can write. I said it in words, but this is correct. Yeah, right.
Maybe this also you can write somewhere at the bottom.
Where?
Rho of e power I alpha psi equal to rho of psi.
Sure.
For all alpha.
Yeah, definitely. Clear? Yeah. I'm not going to give it an equation number because there is some scarcity of numbers here. Okay, so given a curve of unit vectors, smooth curve of unit vectors, at each point this can be thought of as the velocity or the tangent to the curve. Now you can see very easily, because psi is a unit vector for all S, it follows that the scalar product between psi of S and its derivative u at the same S is purely imaginary. It has no real part. This is a trivial. It is similar to what we have seen yesterday. So if you like, I can put it in this form. It is purely imaginary. Now, supposing you take this definition and you ask how does it behave under this phase transformation. Suppose psi at each point is transformed to psi prime by this rule with a parameter dependent phase. How does the velocity behave? It is easy to show. I will leave it as a trivial exercise that the u goes to u prime according to what I have just written. By the way, what is U of S? So anybody just tell me, what kind of object is it? What is U of S? The things we are dealing with are Hilbert space, unit vectors in Hilbert space, ray space. These are the mathematical objects we are discussing. Here I have defined U of S to be d psi by d psi of S by ds, derivative with respect to the parameter. What is U of S? I am asking a trivial question, just want to be sure you are all with me. Huh? It is what? Correct. That's all. That's all I wanted to know. There is no implication or reason to think that it belongs to the unit sphere. Just some vector in Hilbert space. In particular, it could be 0. If the psi has no dependence and it's just a single point, then the curve is a trivial one and U can even be 0. So you see that when you make this phase transformation, we can call it a gauge transformation. When you apply a gauge transformation to the curve, to the vectors psi of S on a given curve, the way in which the tangent U of S transforms is given by this expression 313. It is a linear inhomogeneous transformation law. These are things which one is familiar with in when you study general relativity, for example. So there is a simple way to construct something which transforms in a linear homogeneous manner, and I think I will now rub this part of the board. All you have to do to get rid of this inhomogeneous term is to take this U and take its component orthogonal to psi of S at each point. That is, you subtract from U the part parallel to psi. So let us define it in this way. This is a definition of U perpendicular at each point. So here is this curve C. You can picture U as a tangent to the curve. Unfortunately, the way I have drawn it, it seems to be well, who knows? We don't know in what direction psi is pointing in this picture. So I'm just saying, take the component of U orthogonal to psi, call it U perpendicular of S, and this thing obeys a nice transformation rule. It is linear homogeneous. Okay. Using this simpler transformation rule, we now define a geometrical quantity. We will say that for any parametrized curve in the ray space, we can associate a length with it, and that length will be written as capital L, a functional of this curve in the ray space. And how is it defined? It is the integral with respect to the parameter of the inner product of U perpendicular of S with itself, that is a norm square root. So the integrand is the length of U perpendicular of S at each point along the curve, and you integrate it with respect to the parameter. And you can see, by putting in all the definition of U perpendicular, it can be written more explicitly as follows. So I just recapitulate. You take a parametrized curve up above, projecting onto the given C down below. At each point you compute the tangent to that curve. You project away the component of the tangent in the direction of psi. So you look only at the perpendicular part of u, perpendicular to psi. That has a very, very simple transformation law under gauge transformation. You use that to define the length down here. What you have to see is that you have to appreciate this capital L is really a functional of the curve C here. It does not depend on which lift you use to calculate. Why? Because of this very simple transformation rule in going from a script C to script C prime. You can see that u perpendicular prime is a phase times u perpendicular, so that phase will disappear in the integrand. So that shows you two things. First, several things. So the way to, in practice, compute this length for a given curve in the ray space is to take any lift you like, whatever is convenient, and calculate u of s at each point along the lift, project out the part in the direction of psi pointwise, and then put it into this integral. So two properties are, because it is invariant under these gauge transformations, it is indeed a quantity defined on the ray space. Though for calculation we may use one lift or another. We will see later that the geometric phase has very similar properties, and then you must remember what I am saying now. So the first part is, because of this gauge invariance, it is a ray space quantity. Secondly, it is reparametrization invariant. Now this I will define in more detail a little bit later, but it shows that if you were to change the parameter in a monotonically increasing fashion, this expression, this functional, does not change. Why is it? Because, well, what is the reason? Why is it reparametrization invariant? Is this concept new to some of you, or is it familiar to all of you? Huh? Yeah. It is, to say that it's a length is a definition. What do we mean by saying that it is reparametrization invariant? And why is it reparametrization invariant? That's what I was asking. Huh? No. Yes. How do you know that if you change the dummy variable, this value of this functional will not change? How do you know that? I say it is so, but can you see simply why that is so? I give you a hint. Suppose I did not have this square root here. Would it then be reparametrization invariant? Why? Why? Exactly. Technically what we would say is the integrand is linear, not linear, it's homogeneous of first degree in the velocities. That is the key point. Psi dot, the whole integrand, is first order in velocities, homogeneous of degree 1 in the velocities. That is the important thing. Yeah? You want?
So that's why you're taking the square root in the integrand as opposed to taking the square root of the entire integral.
After doing the integral. Correct. See, because we are doing gauge transformations which vary from point to point. So, if you were to put the square root outside after the integration, you would mess up everything. You must do it inside. Okay. So this is the point, and because so we say it is, we will say it in more precise language a little bit later, but you can see it already. We put the square root inside so that the integrand shall be, it's not linear in velocities, it is homogeneous of degree 1 in the velocities. Now, if you have studied special relativistic mechanics in Landau and Lifshitz' book, do you know how the action for a relativistic point particle is defined? Classical action. What is it? It is integral of, with respect to proper time, the length of the trajectory in space-time. If you were to write it in terms of the 4-vector position as a function of parameter, what does the action, relativistic, free particle, classical action look like? Can anybody tell me? If I take a point in the special relativistic space-time, a point mass going along some path in space-time, so this is like, huh? Yeah, the action, yeah, exactly. What should I put inside? Eta mu nu x mu dot x nu dot, if I am explicit. So if we use covariant and contravariant upper and lower indices, this is the expression for the action for a free relativistic particle apart from the mass, no? In relativistic mechanics. And why is this structure important? This is reparametrization invariant. When you study string theory for the first time, and that's all that I have studied, the famous Nambu-Goto action for a string, same idea, reparametrization invariance. So it's the same thing that we are using in this context. You see here also, if you had put the half after the integration, it would not have made sense. It would not have invariance under change of parameter. It has to be inside the integrand. Okay. All right. So, because it is independent of choice of this parameter along the curve, we give it a special name. This property is named, is identified by saying this is a geometrical object. It's a geometrical quantity. So now I come to a very important notion. Because you have been able to define a length for each curve in the ray space, and here are all its properties. A curve in ray space, given endpoints, let us say rho 1 and rho 2, a curve in ray space with given endpoints is called a geodesic in ray space if this length functional is an extremum, and for our purposes a minimum, which means first order changes in this curve in the ray space, keeping the endpoints fixed. If they do not alter the value of this functional, then you are at a geodesic in the ray space. So how do you, so that's a definition of a geodesic in ray space. I want you to understand this definition carefully. So you can now go through the entire analysis. You can start with this. You can use the principles of calculus of variations or Euler-Lagrange equations, if you like, of classical mechanics. You can derive the equations, differential equations obeyed by a geodesic. And all this you can find in various places. Among other places in our paper of 21 years ago, it is given in complete detail. Annals of Physics, I think the reference will be known, part 1. So I will not go through derivations, but I want to give you all the important facts. The 3-4 things I have to tell you. Suppose you take 2 points in the ray space, I call them rho 1 and rho 2, corresponding to the images of, let us say, psi 1 and psi 2. So this is rho 1, the image under projection of psi 1, rho 2, image of psi 2 under projection. And supposing they are non-orthogonal in the sense appropriate to ray space, that is, the trace of rho 1, rho 2 is strictly greater than 0, which means same thing as saying that the vectors psi 1 and psi 2 are non-orthogonal. Then it is a result there exists a unique geodesic C0 connecting rho 1 to rho 2 in the ray space. Okay. Huh? Which is yeah. I leave that to you. See, this is in the language of mathematics, it is a complex CPn-1. That is what it's technically called. Complex projective space of complex dimension n-1. But remember, this length is a real quantity. So for computation, for getting the geodesic equations and solving them, etc., I find it more comfortable to think of R as a manifold of real dimension 2 times n-1 and work on that basis. Whether you like to say this geodesic is a curve in a complex space of dimension n-1, or you like to express it in other words, I leave that to your convenience and what you find comfortable with. But there is no ambiguity or uncertainty how to define a geodesic. You take this curve, you make small changes in this curve at each point except at the end points, just as you would do for classical equations of motion based on the Euler-Lagrange Hamilton's principle. Except there everything you change is in real configuration, classical configuration space. Here the changes at each point are in going to a nearby point in this space. You must use that properly. What would you mean by a small change? What do you mean by a point rho being altered to a nearby point rho prime? What does it mean? So you must have a clear picture. What is the ray space? What does it mean to go to a nearby point? So actually, you can see very easily, if a certain point rho in the ray space, maybe I go to that figure, if I take a point rho in the ray space, I can imagine it is the image of some psi in the Hilbert space, right? If I want a nearby point, what will I do? I take a nearby point in the Hilbert space within the unit sphere. I'll call it psi plus delta psi, and then I'll take its projection. So this is how I would reach a nearby point in the ray space given a point rho. So this is the sense in which one has to write out the equations of calculus of variations, and you have to solve them. They are differential equations of second order. There are various conditions, constraints, and so on. You must do the whole thing carefully, and then you will find all the results I am now going to describe. I am not deriving. Okay. So first, given any two non-orthogonal points in ray space, psi 1 and psi 2, there is a unique geodesic connecting one to the other, I should say unique shorter geodesic, but I will avoid that. So now, having made that statement, let me now show you how to describe the geodesic from a point rho 1 to a point rho 2 if they are non-orthogonal. That is very important. They should be non-orthogonal. So, for practical calculation, description of a geodesic, it is convenient to say, given rho 1 and rho 2 in the ray space, let us choose psi 1 sitting on top of rho 1 and psi 2 sitting on top of rho 2. That is, psi 1 is some point on the fiber projecting onto rho 1. Psi 2 is some point on the fiber projecting onto rho 2. And you know you have complete freedom in the choice of overall phase of psi 1 and independently of psi 2. Let us make a convenient choice. Let us agree to choose the pair psi 1 and psi 2 so that their inner product in Hilbert space is real positive. It's just a convenience. So I will choose my points sitting on top of rho 1 and rho 2 so that their inner product is not a complex number. It is certainly non-zero. So you can agree that we will make this inner product lie between strictly greater than 0, strictly less than 1. Okay? All right. There is a way to describe this in the language introduced by Pancharatnam, and that is to say, and I will not go into more detail at this point, if two vectors in Hilbert space which are not orthogonal to each other are such that their Hilbert space scalar product is real positive. Remember, being vectors in a complex Hilbert space, in principle, the scalar product of two non-orthogonal vectors will be some non-zero complex number. If it so happens that their inner product is real positive, this property is given a name in honor of Pancharatnam. You can say they are said to be in phase with one another in the Pancharatnam sense. I am not going into more explanation, but let this be in your mind, and at some stage you will understand why this name is given. Yeah. Yeah. Yeah, yeah. No, no. Suppose this is the point rho 1. Maybe I should write it here. Huh? Rho 1 is rho of S1. Rho 2 is rho of S2. What do we mean by pi inverse of rho 1? We mean all these vectors. It is not a single vector. It's a continuous family of vectors differing from each other by phases, all of which project onto the given rho 1. So pi inverse of rho 1, that's the meaning of the symbol pi inverse. It is called the total inverse. See, pi is well defined, unambiguous in this direction. Give me any point in B, it will have a unique image. The total inverse says, if I give you the image, what are all the points upstairs which are mapped into that image? They are called the pi inverse of that image. That's the meaning. So pi inverse of rho 1 is not a single vector, it's this whole fiber. And I am just saying, given two non-orthogonal points in the ray space, let us choose psi 1 sitting on top of rho 1 and psi 2 on top of rho 2 in such a way that they are in phase with respect, they are in phase with one another in the Pancharatnam sense. Okay, I am losing track. Who asked the question? And you asked the question. Okay, sorry. All right. Then, this is the third important point. If we now choose, now I am going to describe the solution of the geodesic equations of motion.
And maybe you may also
Just 1 minute, huh? One. Yes.
so this in-phase is a notion that applies only to the
Yeah.
V, and it's not there
In ray space. Very good. Yeah. This Pancharatnam in-phase concept is to be applied only for Hilbert space vectors, not for ray space points. So since I have not defined it completely, I am not giving a proof of this statement, but I think by osmosis by Saturday you will understand the concept. Okay. So let me say that in this diagram, C subscript 0 is the geodesic. And now I am going to show you what the geodesic looks like. The geodesic in ray space from rho 1 to rho 2, the solution of the equations, the variational Euler-Lagrange or calculus of variations problem coming from this length functional, when you solve those second order differential equations, you find if you want to describe this geodesic, here is a practical way to do it. It has a lift which looks as follows. I think I better write it here. I will first write all the expressions and then I will give you explanations. Just a few more things to write and then I will be able to describe everything. See, these are all in the notes which you will soon get, parts of one equation, equation 3.16, the one after 315. So now let me say in words. Given two non-orthogonal points rho 1 and rho 2, let us choose vectors upstairs projecting onto rho 1 and rho 2 in such a way that the scalar product psi 1 with psi 2 is a real positive number cosine theta, where theta is strictly in the open interval 0 to pi by 2. I am assuming rho 1 is not equal to rho 2. I want a non-trivial geodesic. Then the geodesic, the unique geodesic running in ray space from rho 1 to rho 2 can be described in the following way. It possesses a particular lift which I call script C0, a particular lift where script C of 0 consists of this parametrized curve upstairs in the unit sphere. S is the parameter along this lifted curve, and in particular S has been chosen in the spirit of what is called the affine parametrization. The meaning of that will become clear. Remember, this length is a parameter independent of choice of parameter. So it has been chosen in an affine manner, and what it means you will see immediately. So here is a simple, very special lift of the geodesic down below. So the geodesic itself is the result of applying pi to this curve. Where does this come from? From solving the variational equations, which I am not doing now. So here is the curve up above. Here is the range of the parameter. It is between 0 and theta, theta being determined by this. At each point, its tangent size u0, which means d psi 0 by ds, can be immediately obtained from here, differentiate with respect to the parameter, and you find at each point in this description, with this choice of parameter, affine parameterization, u0 of s happens to be a unit vector at each point. You remember you said in general the tangent vector u of s at any point in a curve is some Hilbert space vector. There is no requirement that it should be a unit vector. The choice of parameter here, the affine choice, is such that u0 of s happens to be a unit vector at each point, but that's just incidental. It is also orthogonal to psi at that point, which means it is equal to the u perpendicular, the orthogonal projection, which I have used in the definition of length functional. So the two are the same. And so the geodesic from rho 1 to rho 2 down below is the image of this particular curve under projection. So here you have a complete description of a most general geodesic. And it is a result of the way, I should not say that way. What is the length of this geodesic? After all, the length is independent of choice of parameter. So it must be determined by what? Just by theta, nothing else. And if you just sit down and calculate, since this u is equal to u perpendicular and it's a unit vector, you will find, if you do it carefully, it is just integral, what is the range of s? 0 to theta integral ds. The integrand is 1. So it is just theta. Okay. So the length of this geodesic is theta. So it means that the distances, if this is used as, in that sense, as measuring distances in ray space, it's quite surprising, I think. I don't have a very good picture of it. This Hilbert space could have been infinite dimensional. Nothing stops you. Ray space then would also be infinite dimensional. But every point in ray space is within a distance pi by 2 of every other point. It's a very strange thing. Is that that's correct? And I can say it, but I can't make a mental picture of it. I suppose it is. See, the thing that strikes one as funny is even with infinite dimensions, you cannot go very far away from any given point. Of course, on the Earth's surface, it is a sphere S2. We know if you give one point, you can't go infinitely far away from there along a great circle arc. Maximum distance you can go is what? 12,000 kilometers or something, right? Half the circumference. So that is understandable. And in S3, S4, yes. Even in infinite dimensions. It's an interesting fact. Somehow non-intuitive. Yeah?
Why is it restricted to pi by 2 and not 2 pi?
This is because the way this parameter has been introduced. We make psi 1 and psi 2 obey the Pancharatnam in-phase criterion.
The two things should not be.
No. First, they should be non-orthogonal. Second, their inner product should be real positive. Because it is real positive and they are unit vectors, it has to lie strictly between 0 and 1.
Because you want to relate it to well from
Yeah, if you like, yeah. So, probabilities. roughly speaking, this is in the sense of Wigner's theorem, this is a transition probability amplitude. So this has to lie between 0 and 1. If you introduce the angle theta in this way, that theta has to lie between 0 and pi by 2. And when all the dust settles, the value of L of C for the geodesic path is theta. So it means that no point in this ray space is more than pi by 2 distance away from any other point, even though the ray space could be infinite dimensional. Yeah.
You are facing the conditions that technically face in the
Yeah, this can always be achieved. Give me 2 points in the ray space which are non-orthogonal. It is always possible to choose psi 1 on top of rho 1 and psi 2 on top of rho 2 such that they are in phase in the Pancharatnam sense. It is always possible. Do you see any difficulty in doing it? See, you choose some psi 1, choose some psi 2. All you know is that psi 1 inner product psi 2 is a non-zero complex number. So that non-zero complex number has a phase and a modulus. Take that phase and stick it to rho 1 or to rho 2 on the left hand side. So, sorry, you're correct, right, psi 1 or psi 2. Because your choice of psi 1 and psi 2 is completely free anywhere along each fiber. And you can take any phase and attach it to psi 2, psi 1, share it between them anyway. Okay. So choices of psi 1 and psi 2 as a pair are not unique. But you choose psi 1 any way you like. Then psi 2 is uniquely determined. Do you see that? How much freedom is there in the choice of the pair psi 1, psi 2 obeying the Pancharatnam criterion? A single U1 freedom, not U1 cross U1. That is the important point. Okay. And now the last thing I wanted to say is that this C0 is a particular convenient lift of the geodesic from ray space up above, and the most general lift would be of the form okay. So this is my equation 316. It comes in 3 parts. So the point now is, oh my God, it is taking more time than I thought. So the point is that, so I have tried to convey to you the idea of geodesics in ray space, and later it will become the metric tensor in ray space, which is what you are interested in, I know that. So the idea of length can be given in ray space, from that the idea of geodesic, and here is an explicit description of the most general geodesic in terms of a convenient lift. Now once you have one lift, suppose this was the lift C0, any other lift of the geodesic would be related to this particular one by some phase transformation. So it is just a convention that any lift of a geodesic in ray space is called a geodesic in the full space, in the unit sphere B, at the vector space level. So all curves in the unit sphere which project onto a geodesic here will be called geodesics in the sphere B. Just an agreement how to use the language. Yes. Where? In the ray space? Yeah.
You would get the number L of that, which is greater than
Yeah.
and
Yeah.
does not have a bound in the sense of.
Yeah, you can make the, see, you can keep going all, What is you have some funny way of expressing it?
Well, I think
Yeah.
all roads lead to Rome,
Yeah.
even though there is a geodesic rule.
Yeah. Yeah.
But you may decide never to reach Rome, but continue to travel.
Yeah. So there is no upper bound to the possible value of this functional. That is clear. The simplest thing is go once by geodesic, come back, go again, come back, go again, any number of times. So that is correct what you say. There is no upper limit to possible lengths. But I still tell you, I feel a little odd that this idea of length in the race space is such that no place is too far from any other place. Somehow it seems odd to me. But if some of you don't have this kind of difficulty, I appreciate it.
Before you arrange,
Yeah.
can you make some comment?
Yeah, sure.
No, I think this is probably the most important part of this course for students who are listening and coming across it for the first time.
Yeah.
So I want to make several
Yeah, sure. Yeah.
remarks.
Yeah.
Please correct if any of them sort of overreach and to the
Yeah.
level of becoming wrong.
No. Yeah. Go ahead.
First of all, I mean, you said this LC is geometry.
Yeah.
And anything that you define as a function of this C will be geometric.
Anything which I define.
Yeah, because anything that you define in race space is geometric for your purpose.
I would.
Well, let me
Okay.
just complete
All
that
right.
statement.
Yeah.
But in that definition of LC,
Yeah.
on the right hand side,
Yeah.
the quantities don't live in
Yeah.
R,
Yeah.
they live in B.
Yeah.
So always the calculations are done at the
Yeah. Correct.
level of B,
Yeah.
and then you have to make sure that this gauge invariant,
Yeah.
so that it is really a
Yeah.
genuinely a functional of
Yeah.
what is happening at R.
Yeah. Correct.
So when you say it is geometric, what you mean is it's really a functional of what is happening at R.
No. Sorry. When something belongs to R if it is gauge invariant, basically.
Something
Is any object you are interested in, you can say it belongs to the race space if it has the gauge invariance property.
that's correct. And if
It-
it is gauge invariant, you will call it geometric.
No,
Oh.
this is the point. So it is called geometric if it is independent of parametrization. So for example, suppose I had written this expression without the square root. It is gauge invariant, but it is not geometric, because its value will change if I if I scale the parameter. So you might say it is scale invariant, then it is geometric. But the technical word is reparametrization invariant. That is the point. Yeah, next point.
The next
Yeah.
comment is, so we are in days when prime ministerial candidates are very proudly talking about their chest measurement and things
What?
like that. So now some students are getting feeling that you can live things in so many ways. But I think the real thing is the action. The genuine quantum mechanics is at the race space.
Yeah.
That is
Yeah.
where states live,
Yeah.
not really in the
Yeah.
space. And computations, one is comfortable doing only at the
Yeah.
input space level, so
Yeah, yeah.
therefore you have to lift and project. And
Yeah.
that's
Yeah.
a necessity.
Yeah.
And the third comment
Yeah.
is even, I think I would like to suggest to
Yeah.
everybody that concretize these things to just two-dimensional input space.
I'm going to do it in a
Ah,
moment.
okay.
Yeah.
And
Yeah.
okay, now if you are going
I'm
to do
going
it,
to,
I
yeah.
was going to suggest
Yeah.
that before one goes further,
Yeah.
I mean, if
Yeah.
things can be seen clearly in
Yeah.
two-dimensional input space,
Yeah.
then at some stage, one
Yeah.
will find that it's not really, doesn't get terribly more complicated.
Correct. I'll give examples in just a few minutes. I also want to make a request. If you can make a mobile phone call to the canteen that we will all come a little bit late today. Because I see when we stop at 1 and walk up there, still the queue is very long. And they serve up to 2 o'clock. So today I would like to use. I can survive. I would like a little extra time today. Okay, so in this mathematical interlude, here is the last item. There will be another mathematical interlude later in this course of lectures, and this mathematical interlude is the definition of a geometric object called a one form on the space B. I do not have the time in this set of courses to tell you what is the meaning of a one form, but by looking at the examples and how we handle them, you will understand at least intuitively how it is to be understood. The formal expression, remember psi is a general unit vector in the Hilbert space, so it is a point on that unit sphere script B. The formal expression minus I psi dagger d psi, it is a geometrical quantity. It is called a one form on the space B. And later on I will show you exactly what it means, but for the moment just accept this. Then you can say, if you take any sufficiently smooth curve up in the unit sphere B, there was an equation I wrote earlier, 3.12. I don't know if somewhere it is there. Oh well, anyway, yeah, you keep equation 3.12 in mind, then you will find the expression I am writing now this expression along any curve, smooth curve in Hilbert space, in the unit sphere on Hilbert space, as we know this inside is pure imaginary, so if you collect all the factors of I and so on, it is this thing where u of s is d psi by ds, and this expression is completely real. And you also see it is reparametrization invariant. There is no need for a square root anywhere, because the integrand as it stands is not just homogeneous of degree 1 in the velocities, it is of degree 1. It is linear in u of s. So this thing is a number associated with the curve C. It's a geometric quantity. It does not depend on how you parameterize it. And this is, in the language or notations of differential geometry, it is written as the integral of A along the curve C. This is the differential geometric notation for it. So you can roughly see what is involved. If I were to use this expression formally here, I would have to say this is minus I integral along C psi dagger d psi. That's what it would look like. So to make things more familiar, you divide by s and ds and multiply by ds. Then it will be integral ds psi of s dagger d psi of s by ds. And all you have done is to just cancel away the ds's. Okay. Alright, so this is the last thing. This thing called a one form, it will play an important role later on. And what you can see is that this one form, its integral along any curve is the dynamical phase, part of the geometric phase for that curve. So the dynamical phases are described by and calculated with the help of this one form. Okay, I will stop at this point for the mathematics. Now I must go on to other things. Now we will see this one form in more detail little later on. So at this point I like to make some general comments. What I have tried to explain to you is a general mathematical framework involving a Hilbert space, complex Hilbert space of some dimension, the unit sphere in this Hilbert space, and the corresponding quotiented U1 quotiented ray space. So this set of three things is the appropriate mathematical background in which to discuss all matters of Berry phase, geometric phase, etc. And it turns out this framework is all that is needed to discuss geometric phases in quantum mechanical situations. It is also adequate to discuss and handle geometric phases in all classical wave optical contexts. And this is something we have recently written in some detail in a very pedagogical way, because there was some hint in the literature that for classical wave optical situations, general situations, to discuss the idea of geometric phase, one may have to use a framework different from this. So our main purpose in what we have recently written is to say that this is a kind of universal framework for geometric phase ideas. So this framework of three mathematical spaces: complex Hilbert space, which is a linear vector space; unit sphere, which is not a vector space but a subset of H; and the ray space, which is also not a vector space. This is the foundation on which all geometric phase ideas have to be considered. So this is important, and the concept of geodesics, which I have described now, is also very important. And as we will see later, from the geodesic idea we will be led to a Riemannian metric in the ray space called the Fubini-Studi metric. I will describe this later on. And this is that quantum tensor, I think, which you have been interested in. So I'll give you quickly two examples. Suppose you take the two-dimensional Hilbert space, which you would use for a spin half particle or a two-level atom or whatever it is. I just remind you, what would be your description of the unit sphere in the two-dimensional complex Hilbert space? Can you tell me what the script B looks like in this case? Anybody? It's a very well-known, very familiar geometrical object. Yeah? Huh? No. Let me give you a hint. This is a two-dimensional complex Hilbert space. All right. So you will write a vector in this Hilbert space as a column vector with two components. Give them some names. What would you like? Alpha and beta, is it all right? So what is the condition on the complex numbers alpha and beta to get a point in the unit sphere? Huh? So what is it in terms of alpha and beta? Mod alpha squared plus mod beta squared equals 1. Alpha is a complex number, beta is a complex number. So alpha has a real part and imaginary part, beta real part, imaginary part. What does this condition say? Sphere where? Huh? Yeah, it is the sphere S3 embedded in Euclidean 4-dimensional space.
I mean, if I look, can you write the thing down how
Yeah.
We are so important.
Alpha and beta are complex numbers for this two-dimensional Hilbert space. Alpha 1 is the real part, alpha 2 is the imaginary part, etc. And how do you get a point here? You have to put a condition. On 4 real variables, you have to put this condition. Huh? In R4. So, yeah, correct. So, let us, in fact, write it like that. Huh? Yeah, yeah, sure. Yeah. Yeah, yeah. Yeah, yeah. Yeah. It is, he had answered it earlier. If you have a curve drawn in the unit sphere B, smooth curve, differentiable curve, at any point you can ask what is the tangent. Tangent is a vector in Hilbert space, but it need not be a unit vector. Now you just look in ordinary physical three-dimensional space, the surface of the earth, you draw latitude circle or longitude circle, and imagine you are going at high speed along a longitudinal circle, a great circle. Then what is the tangent vector at any point? It will point from here to the moon or somewhere else. Depends on how fast you are moving. The tangent vector can have any length. So you can. So the key point is, and which we will do later in the second mathematical part, given this manifold B, how do you describe tangent vectors to be at each point of B? It is called tangent space to be at each point. That we will describe later. But since you have asked this question, it's a very nice question. If the earth were a perfect sphere, and you take some point on the earth, on S2, what is the tangent space to this earth at that point? Geometrically, can you tell me? Huh? What, at Chennai, if it was a perfectly smooth S2, the earth, what would be the tangent space to the earth at Chennai, at IMSC? R2. It would be a plane, infinite vectors of all possible lengths, real vectors. Okay? And that would just be touching the earth at Chennai or at IMSC. Correct? So that analog of that in this case, we will have to develop. Tangent space to this manifold B at each point of B, which I will do later. But this is the idea. So, okay. So this is done. And then.
Long back, long back you would have answered this question. Actually, I don't
Yeah.
see what was this question.
Yeah.
On B does not mean an element of B.
Yeah.
You would have answered 35 years back.
How many?
35 years back.
Yeah. You are reminding me of my age.
On B for an element of B, right? Yeah. That was.
All right.
No, but your question.
Yeah.
You had sort of mistaken on B to be an element of B.
Yeah. You were not born, Fock was not with born. Okay, so in this case, what is the ray space? Well, in the mathematical notation, it is called CP1, and this is the Poincare sphere. Okay? This, I'm not going to prove it, many of you may know. If you don't know, you must learn it. And the other significant thing which I must say is that the ray space geodesics which we have described in the rubbed out board are the same thing as great circle arcs on the sphere S2, Poincare sphere. Okay, the two are the same. Okay. So, and well, angles are measured differently. So, with the usual way in which we define latitude and longitude in radian measure on the sphere S2, the distance between 2 points on S2 can never exceed pi in the usual way in which we measure or define spherical polar angles. So, there is a half difference between that and what I described earlier. Next example, I will not go into too much detail. I will just give some indication. You might ask, if we go from a 2-dimensional Hilbert space to a 3-dimensional Hilbert space, what happens? It's a very natural question to ask. Well, what is the unit sphere B in this case? Well, we have seen what it is in the previous case. What would you say in this case? It's very simple. Now, what is B? Huh? S5, exactly. So, it is the unit sphere in 6-dimensional real Euclidean space. That is trivial. The ray space, in the mathematical notation, it is called CP2. It is complex dimension 2, real dimension 4. It is rather difficult to picture. Many years ago, some of us took the first steps in this direction of trying to understand the structure of the ray space in this case, and we made some progress. I don't have the time now to give you the details. That was 1997, 95, something like that. But a couple of years ago, Simon, Singh, and some more, who are the other authors, you have done a.
No, I am not.
You are,
I am not.
Sandeep and Singh and Neeti. And Neeti also, no? Neeti and Sudha also.
Neeti and Sandeep.
Yeah, they have done a very, very detailed analysis of this three-dimensional Hilbert space. What does the ray space look like? It is not at all as simple to visualize as this Poincare sphere. I may give you some idea about it later on. Let us see. But I just want you to appreciate this HBR framework is very important for all geometric phase calculations in quantum mechanical as well as classical optics situations. But even when you go from 2 to 3 dimensions, it becomes quite difficult to visualize.
This is an understatement.
I see.
Say that HBR structure is the basis for geometric space is an understatement. That is the basis of quantum theory. I mean, even if one is not interested in geometric spaces, but still one must know this.
Sure. You're right. I agree with you. I apologize. In the first lecture, I said in this course of lectures, we will go back to many familiar concepts of quantum mechanics. We will revise them, we will refine them. So that was what I had in mind. I agree with you. So keep this as a very basic foundation. When people describe probability, classical probability theory, there is a thing they say, the foundation of classical probability theory is a triplet. You must have seen this any number of times. In that same spirit, I won't tell you what this triplet is. In the same spirit, you can say, for all quantum mechanics, this is a basic triplet. Okay, so now I have enough mathematical background to tell you what is the generalization made by Samuel and Bhandari in 19...
I think I will go back to some comment that I made that students must look at the two-dimensional case.
Yeah.
Not exactly this. In addition, this expression that you gave for geodesy, that they should be able to derive it at least that particular case. Then it will become very general.
Correct. So I leave that as an exercise. So now you remember that so now the mathematics for the moment is over. I come back to the geometric phase development. We saw that compared to all the assumptions made by Berry in his original work, Aharonov and Anandan showed you don't have to make the adiabatic hypothesis even for non-adiabatic situation. If you have any cyclic solution of any Schrodinger equation, you can define a geometric phase. So this was their important achievement. Plus I also said they showed that the geometric phase is something belonging to ray space. This is also something which was achieved by them. The next step taken by Samuel and Bhandari the very next year was to show that the cyclic condition is also not needed to define geometric phases. So remember all the 4 conditions which Berry assumed were valid. One by one they have been relaxed. Aharonov and Anandan say we will only use cyclic condition, not on the Hamiltonian but on any solution to the Schrodinger equation. We do not have to use the adiabatic condition. Then these two, Samuel and Bhandari, come and say we don't even need to have the cyclic condition. So in other words, it means that you give me any time dependent Schrodinger equation, you give me a solution of that from one time to another time. It can be an open evolution in Hilbert space. It is not, does not have to be cyclic as a solution. Psi of capital T need not be phase times psi of 0. Even then we can define a geometric phase for such an open evolution. The main thing that they used is the following, and I will write an equation. And suppose you start with some geodesic in the ray space which I have described in the previous boards, and then you have this special lift of the geodesic to the level of the unit sphere, and then you have general lift. I suppose I should not say in, but I should say to, right? So then let us suppose that you have any curve in B, script C, whose projection is a geodesic. That is all that is required. Then they showed a certain result. I will now write it in this symbolic form in the language of differential geometry, and I will also write it in explicit form. Here is a result which they have found. I will just write it and then I will describe it. They showed that you take a geodesic in the ray space, lift it up here, and you can take any lift you like. So this lift, general lift of the geodesic, will go from a point, a vector psi of 0 to psi of theta. I am using the affine parameter for the parameter S. So the range of S is exactly 0 to theta. So what they showed is that the argument of the scalar product between psi of 0 and psi of theta is equal to the integral of the one form A along your lift. Okay? If you change your lift, this integral will change, this will also change, but the equality will always remain. So, I would like you to look at Samuel and Bandari's paper in some detail, and they make a claim. This is the most important result of their paper. That is a statement made. So now they say the following. So this is a property of geodesics proved by them. And to give full credit to Samuel and Bandari, first, in that year they had 2 physical review letter papers. The first was an experiment, a laser-based experiment to verify Pancharatnam's 1956 theory. The second was this theoretical paper, and they were the first people, as far as I know, to bring in the concept of geodesics in ray space in this context. The Fubini 2D metric, all this, as far as I know, they were the people. Aharonov-Anandan did not have it, Berry also did not have it. And I don't think the other Simon had it either, right? Barry, Simon, I don't think so. So here is what they do. How do you define the geometric phase for arbitrary non-cyclic evolution via the Schrodinger equation? So here is what they do. So you have some Hermitian Hamiltonian, possibly time dependent. Let us say a solution is given to you over some stretch of time, and this we will say is giving you a curve C in the unit sphere B, okay, up above. So now they say, so if I were to draw this curve, here is psi of 0, here is psi of t, and this is the result of solving some Schrodinger equation from one time to another. Then they say, having come to this psi of t, return to psi of 0 via the unique geodesic connecting them. They have introduced the concept of geodesics, they now exploit it. So then they say, you define, sorry, you take this Schrodinger evolution from the Schrodinger equation from time 0 to time capital T. This is what I have called C up there. So the script C in general is an open curve in B, and then you attach to it any geodesic from psi of t back to psi of 0. So this is a prescription. Then you see this C prime is this fellow followed by the return path. It is the return that has to be geodesic. It is the forward which is Schrodinger evolution. So C prime is a closed loop in Hilbert space, and they then use this construction to say the geometric phase for non-cyclic Schrodinger equation from psi of 0 to psi of t shall be the same as the closed loop integral of the one form A. Not any. This is a unique geodesic from psi of t to psi of 0. Any lift of the geodesic. So that's what I meant.
You're not in the R.
No, yeah, this is at the Hilbert space. So remember, the geodesic here is unique, and all lifts of a geodesic by convention will be called geodesics at the Hilbert space level, at B. So you have freedom in the choice of the geodesic up there. So you can, so as you pointed it out, I should have said, this can be any geodesic curve. Any lift of the unique geodesic down below. So I will not prove it or do any such thing. I hope I have given you the ideas with which these two people are playing. To understand the details of their argument, it is good that you see their paper. And in particular, you must decode what they have written to see what role this equation plays in their definition of geometric phase. So I summarize what they have done in the following way. They introduce the concept of geodesics. That's a mathematical idea. They prove a certain relation valid for every lift of any of a geodesic. This is their, and it is said in the paper, this is the most important result of the paper. So this result is used as an input to define geometric phase for non-cyclic evolution. This is, so I am just paraphrasing what they have done. Exactly how it is true, is this a reasonable definition, etc. I leave it to you to look at their paper and understand it. Of course, this was written in 1988. This is what, 26 years ago. Yeah. But some of the statements made, maybe they were in a rush to do it quickly. They could have expressed it a little better. That's my feeling. Okay. All right. So with a few more minutes, with these two, the Aharonov-Anandan and the Samuel Bhandari work, we see that geometric phases can be defined in this quantum mechanical background without the adiabatic condition, without the cyclic condition. Two things which are crucial in Berry's original treatment. And there was one more thing I wanted to say. It is escaping me at the moment, unless I have written it here. Okay, if it comes back to my mind, I will tell you. So now, so I come to section 4. This is the work of Simon and myself in 1993, 21 years ago. And this is what we call the kinematic approach and the role and the properties of the Bargmann invariance. So we can say this is the third step in generalizing Berry's original work. Berry, Aharonov-Anandan, Samuel Bhandari, and ourselves. The key point in this was to consider on these parametrized curves in the space B, two groups of transformations. One group of transformation we have already seen, changing the phase of psi of s at each point, and that we called it a gauge transformation. The other is the reparametrization, change of the parameter s in a controlled manner. So I will describe, since gauge transformation has already been shown on the board, I will not repeat those equations. I will tell you what reparametrization means, what a transformation of that kind means. And once we have these two groups of transformations acting on a curve in the space B, one can ask, what is the simplest expression you can construct involving a curve which is independent, invariant under gauge transformations, invariant under reparametrization. That was the key motivation. So I will now define the reparametrization transformation. So gauge transformation we already know. Now this is what we mean by a reparametrization. You take a vector, a curve of vectors psi of s, and then you relabel the points. You imagine that you are using a different clock or a different length scale to measure where you are along the curve. You allow the parameter s, which was parametrizing the points of the original curve, to be replaced by f of s. Call it s prime. The condition is that f of s should have a its derivative at every point should be greater than or equal to 0, which means this is called a monotonic reparametrization. So when you do this, what will happen is that you are going through the same set of points in Hilbert space, but you are giving them different parameter names. That is all you are doing. Similarly, if this was the image in ray space, C, capital C and capital C prime, you end up with a reparametrization of the points at the ray space level. The set of points is the same, but the value of the parameter you attach to each point is changed by any such rule. No. So the initial value S1 will be replaced by some S1 prime, which is f of S1. S2 will be replaced by S2 prime, which is f of S2. Everything is permitted. Okay. So now you ask, what is the simplest expression you can construct out of the vectors psi of s along a curve C, such that both under gauge transformations, change in the phase, and under change of parameter, the expression does not change its value. And here is that expression. I think I will probably stop at this point today. I will first write it and then justify the notation. I think I will use space here. So this equation 4.2 is from here onwards. So this involves a little bit of work, not very much, not very difficult. The simplest expression that you can construct, reasonable expression I can say, given a curve C, is to construct two separate quantities. One thing called the total phase, and that is the phase of the inner product of the endpoint vectors. Psi of S1 is psi of S2. It is in general a complex number, and this will be called the total phase associated with the script C. And the other part is this dynamical, which I have written there, which also is something to be computed with script C. And the statement is, you take the first part, total phase, subtract from it the dynamical phase. This difference is reparameterization invariant, gauge invariant. Because it is gauge invariant, you can say it is a functional of the ray space image only. So it does not matter what script C you use to compute the individual terms, the difference will always be the same. If you change the lift to C prime in both, the left hand side will not change. So this is the result of the gauge invariance. The reparameterization invariance here says what you have constructed is a geometric quantity. And the reparameterization here is trivial because it is linear in the velocity, in the tangent vector. Okay, so this was our construction. I am saying that apart from trivialities, it is assumed that the endpoints psi S1, psi S2 are non-orthogonal. That is, yeah.
What does reparameterization involve in both?
Beg your pardon?
What is this reparameterization involve?
The fact that this whole expression is independent of the choice of parameter entitles you say this is a geometric quantity. Geometric quantity. The fact that it is invariant under gauge transformations, change in the phase at each point, entitles you to say it belongs to ray space. These are two independent attributes of ray space. Yeah. The ray space belonging to ray space means unchanged by gauge transformations. Being geometric means unchanged by change of parameter. Yeah. So there are two distinct things. That is very important. So what I want to just couple of things, and then it's a natural stopping point, because then tomorrow I start with Bargman invariants. So this is our definition of the geometric phase, and the thing I want you to appreciate is that right at the start, the very definition of this object is for an open curve. You don't have to have a closed loop. So you can see that, first of all, I hope you appreciate, once your input ideas are given, the expressions are very elementary. Checking these properties of these two invariances is actually trivial. So to calculate the geometric phase for any open curve in ray space, take any lift, calculate phi total, calculate phi dynamical, subtract. So you have infinite freedom in the way you actually calculate things. Now I can make a connection to the two derivations of Berry we gave yesterday. The fact that we have infinite freedom in doing the actual calculation, the reflection of the fact that my first version of Berry's result and the second version of Berry's result, there are slight differences. Remember, in the second version we said in the parameter space things should be globally well defined. In the first derivation I gave without using parameter space, I did not have such a condition with respect to time. That is a reflection of the flexibility in choosing the lift and calculating the pieces on the right. Once calculated, the difference will not depend on which lift you use. That is very important. So any lift of a ray space curve can be used to calculate each piece on the right. Infinite freedom. And I think Simon also mentioned this infinite freedom yesterday. Second point I already said, it does not take special effort to define this object for an open curve, for a non-cyclic evolution. The first thing you can do is this. That's very, very easy. Second, third, it is purely kinematic. There is no Schrodinger equation, there is no Hamiltonian. Okay? So it is just something based on our HBR framework. So any Hilbert space, it may occur in any context. It can occur in classical optical context, polarization optics, wave optics, anything. If it has those ingredients in it in a natural way, this definition is relevant. Okay, and now I will make one statement and then maybe we can stop. This is something I like to tell you in a little bit detail. The definition of geometric phase is, I repeat, really quite trivial. Very easy mathematics, nothing complicated at all. You just have to know what are the mathematical and geometrical objects you are dealing with, what are the transformations you are applying, and you are looking for invariants under those transformations. So it's really very simple. Having defined the geometric phase for any curve in ray space, it is a trivial result to show if your curve in ray space happen to be a geodesic, its geometric phase is going to be 0. This is also trivial. I will leave it to you to check with the earlier equations why this is trivial. So I want to repeat, this is trivial. Now we compare what we have done with what Samuel and Bhandari did. I told you there was one equation in Samuel and Bhandari's paper which they say is the most important result of their paper. Its content is the same as this statement, but it is not presented in this way. They prove a certain property for geodesics. The mathematical content, I tell you, is this same thing written in a certain way, but they use it in the process of defining geometric phase for non-cyclic evolution. That is the spirit of their work. Here, the definition of geometric phase for arbitrary, non-cyclic, non-Schrodinger evolution is there. This is derived as a consequence of the definition of geometric phase. So I hope you see the difference in the spirit. For Samuel and Bhandari, this thing expressed in the way I wrote earlier is a step in the definition of geometric phase. For us, it is not so. Geometric phase is defined independently. This is a very useful, very easy consequence. That is what I want to stress. So, because this we are going to use in the discussion of Bargmann invariance from tomorrow. So, I think I will stop here. I appreciate your allowing me to run along. If you want to make any comments.